Hello and welcome to this lecture. We are now going to see this very interesting idea of eigenvalues, eigenvectors and upper triangularization. It was the end of last lecture. We saw that we may not always be able to get a diagonal matrix for a linear operator. There may be some limitations because you may not have enough eigenvectors. But it turns out upper triangularization is always possible for any linear operator. There is an upper triangular matrix. So that's the sort of the main result we'll see. Along the way, I'll also point you out other computational tools, numerical computational tools. In particular, I'll talk about Sage Math and a notebook that I sometimes use for Sage Math, and then MATLAB also, a little bit towards the end. So that's the agenda for this lecture. Let's get started. So here's a quick overview. The last bullet probably is most important. Basis of eigenvectors results in a diagonal matrix for the operator, and one sufficient condition for having a basis of eigenvectors is distinct eigenvalues. We will see that that's not the only, we saw already that that's not the only way. There are other matrices for which may be diagonalizable, which may have a basis of eigenvectors in spite of having repeated eigenvalues. We may not be able to completely characterize those things in this lecture. We will study more as we go along. But let's look at upper triangularization. This lecture is mostly about upper triangularization, and that is possible for any operator. Okay, so let's see that. So the crucial idea is the connection between invariant subspaces and matrices of operators. How do invariant subspaces affect the matrix of operators? We saw that when there is an entire basis of eigenvectors, the matrix becomes diagonal. But supposing you don't have that, you have just some invariant subspace, then what happens? Okay, so here's an example I've taken. You have an operator T from V to V, and then there is an invariant subspace for V. U of V is invariant under T. Of course, when I say invariant subspace, I mean invariant with respect to T invariant subspace. Okay, we know we can pick a subspace W so that V is U direct sum W. We know that that's possible. We can come up with a basis for V, which will first have a basis for U and then the basis for W, right? So that's possible. We can do that also. Okay, because it's a direct sum. So now, if you think of the matrix of the operator in this basis, you will get something slightly interesting. You will start seeing some zeros. Why is that? Because, you know, in this basis, U1, U2, Uk, W1, W2, Wn minus k, if you want to find the matrix, the first column is TU1 expressed in terms of this basis, right? So TU2 expressed in terms of this basis, so on. You go up to Uk and then W1 to Wn minus k. I'm not saying anything new here. So now let's closely look at what happens because of the invariance of U. If you look at TUI, it will have coefficients from U1 through UK. There will be some coefficients A1i multiplying U1, AKI multiplying UK. Okay, it could have. But because it's invariant, TUI belongs to U, right? TUI belongs to U. Since it belongs to U, it cannot have anything from W, okay, because of this direct sum property. So it's all these guys should be 0, okay. So these zeros have to show up for every UI. Is that okay? So remember once again, see, I'm going to write coordinates for TU1 in terms of this basis. So in this matrix, this first guy will be U1, second guy will be U2, UK, and then W1 will come, Wn minus k will be the last row. Okay? Imagine, right? So every row you can associate with one of these basis elements. So that's the coordinate corresponding to U1 in TU1, right? So that's how we write this matrix out. So all these bottom n minus k coordinates have to be 0 in the first k columns. Okay, that's because of the invariance of U. Okay, that's very nice. Okay, so invariant subspaces, if you pick the basis, they help you pick a basis in which at least quite a few zeros are guaranteed. Okay, and this is crucial idea, and this was also used in eigenvectors and all that. Here is the connection. I've written it down cleanly for you, right? So you have these A's which give you, the invariant part of the operator, and then you have a bunch of zeros. After that, you will have the TW1, TWN minus k. I don't know what's going to happen there. When you do TWN, it may have something in U, it may have something in W also, right? T times W1. Okay, after I have transformed the W basis of W with T, it could have both components in U and W also. I don't know. This could be a full matrix, but here I will definitely have zeros. Okay, so that's the form for the matrix. Okay, if you assume that this vector space V is over the complexes, then I know that there is an eigenvalue. Okay, so invariant subspace, this is for a general invariant subspace. Let's focus on eigenvalues, right? So eigenvalues, we know they exist definitely if you have complex field. So let's say we have complex field and there is an eigenvalue lambda. Now this lambda V1, this V1 is a one-dimensional, I mean it's a span of V1 is a one-dimensional invariant subspace of T, right? So that's this relationship. We know that eigenvalues, eigenvectors correspond to one-dimensional invariant subspaces, okay? So let's use this idea here, right? So you take the invariant subspaces basis V1 and then pick W1 through Wn minus 1 to extend it, right? So or pick a W which will give you a direct sum of V and you get a basis there, okay? So now let's say T times Wj, it will have something in V1 and it will have W1 through Wn minus 1 also. But what about T times V1? It will only have V1, right? So T times V1 will only have lambda times V1. So the coordinates in this basis, right? Coordinates in this basis will simply be lambda 0, 0, so on. Okay, same idea. So you have lambda followed by a bunch of zeros, but here I will have lots of non-zeros, right? So nothing one can do about it. You will have lots of non-zeros. Okay, so this is, I mean, already it's telling you how to do zeros, and let's attack this part separately, right? So we'll attack one by one. We have at least got a bunch of zeros in the first column the way we want. Remember, I'm going towards upper triangularization, so this is a good step for me. Okay, so let's see if we can do any further. Okay, so as I describe this procedure, I want you to remember another upper triangularization that we did. Okay, what is that? That's using elementary row operations, right? We were able to quickly and very easily using elementary row operations do upper triangularization. So here we cannot quite do that. When you do that, then the basis changes, no? Input output basis ends up changing. I don't want to do that. So I have to only do this eigenvalue business, okay? And only do change of basis. Every time I need to do a change of basis, I need to do a similarity transform, right? S inverse AS. That's the only thing I'm allowed. And whenever I do this, find a basis, find an eigenvalue and then do a change of basis, that's okay. Change of basis is okay because I'm not changing, I'm changing basis on both sides, okay. If I do elementary row operation, then I'm changing basis only on one side, and that's not what we are working with currently, okay. So this is interesting, but this process will be sort of like that, you'll go one after the other, sort of like pivoting and all that, but we're using similarity transforms, finding eigenvalues and doing things like that, okay. Okay, so I promised I will show you a few other tools. And this is a tool which is it's a Sage Math notebook called CoCalc. It's I mean, it also offers free accounts. You can also get paid accounts if you like. I use that sometimes when I want to use Sage Math. Okay, and this is syntax in Sage Math. Sage Math will have its own syntax. See, the thing about all these tools is every one of them has its own syntax, its own functions. They're all sort of similar. They will have the same sort of answers at the end, of course. But you should get to know the tool more and more. And once you know one tool, usually other tools are also easy. Okay, it's just the principles are the same, right? So it's just the names end up changing. Okay, so Sage Math, for instance, you can declare a matrix like this. Now this is a very, very, very carefully curated matrix. It may not look like that to you. It might look like I have numbers all over the place, but this is a matrix I have very specially chosen. Okay, so it's a very curated matrix, but you can also work with general matrices. Even in Sage Math, there is a random matrix function. You can generate random matrices and work with that, etc. And you can see how it works, right? So you can define a matrix, put a semicolon, I have to put an A for it to print. Okay, Sage Math works like that, so that it prints. Otherwise, you have to print it explicitly. You call that. So this is my matrix, 5 by 5 matrix. In Sage Math, A dot eigenvalues prints out all the eigenvalues, and you see eigenvalues are 55, 55, 55, 55, 55. This wouldn't have happened by magic, right? If I were to put random numbers here, it's very unlikely you will get 55, 55. Okay, so this is again just an example to show you, right? If I put 55 on the diagonals and it's a diagonal matrix, you will immediately believe me that all the eigenvalues are 55. But here is a matrix which looks so different from the diagonal 55, right? All over the place there are numbers, but its eigenvalues are just 55, 55, 55, 55. Okay, that's interesting. And then there is this write business that you have to do in Sage Math, right? So if you this command A dot, notice the structure, right? It thinks of A as some object and it puts methods on the objects. And for those of you who have background in computer science, you'll see what I'm talking about. So it's sort of an object-oriented sort of thing. Okay, so it's very different. So this method eigenmatrix underscore write, and then 1. I mean, why 1? Because eigenmatrix underscore right actually returns what Python calls a tuple. I'm interested in the second thing in the tuple, so that's 1, and that's this matrix. So notice what has happened. There's only one eigenvector. Okay, there are 5 eigenvalues, 5 repeated eigenvalues, but there's only one eigenvector. Remember, 0 and all is not eigenvector, right? So there's only one eigenvector, and it looks very simple, right? 1 minus 4, 7, 8 minus 6. Okay, so it's there's one eigenvector, but I know there'll be one eigenvector, right? Any matrix, I mean, complex. Okay, these are numbers. So I know eventually I can go to complex numbers. So I will have one eigenvector. That is guaranteed. Okay, once I have this eigenvector, what is it that I can do? I can make a change of basis. How do I do a change of basis? I have to come up with this matrix S, where every column is my basis, the new basis I want to go to. I have my first vector, which is the eigenvector. Okay, 1, minus 4, 7, 8, 6. How do I pick the other ones? I simply extend. Okay, I know how to extend, right? I just pick the standard basis. 0, 1, 0, 0, 0, 0, 0, 1. I extend like this. Okay, so this column matrix is a construction in Sage Math. It just lets you define one column at a time and put it all in one line. Okay, so it's just a simple way to construct a matrix. Again, you see, this is my S. I've prepared my basis transformation matrix. Once I do that, I have to implement my basis transformation, and that's what I've done here. Again, there's this method called inverse. So if you do S dot inverse, I mean, you can see, I mean, those of you who have experience calling these methods, you'll see that open bracket, close bracket clearly tells me that there's a function here. So S dot inverse, so computes the inverse, multiply by A, multiply by S, you will get this matrix, and lo and behold, you know what's going to happen, right? So the first one was an eigenvector, so I got the first column 55 bunch followed by zeros, remaining I don't know what it is, right? So it's all over the place, I get all sorts of entries. Okay, so this shows you how this worked. Okay. All right. So it turns out what we did for the first column, we can continue. Okay. I'm going to come back to this sheet and show you, and I've actually continued that. But let me first write down or show you, describe to you the principle behind how to continue this, transformation beyond the first column, go to the second column, get a bunch of zeros there, etc. Let's look at that next. Okay. So this is how you proceed towards upper triangularization. So we saw before that there was this first column, which is lambda. See, remember, I've come to this state, right? I've come to my matrix being, lambda 0, and then there was this b 0 1 to b 0 n minus 1, and then b 1 1 to b 1 n minus 1, dot 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 b n minus 1 1. So this is my matrix, right? N minus 1 n minus 1. Okay. So I'm going to sort of split this like this. Okay. So this corresponds to V1, and these guys are all W1 to Wn minus 1. So I'm thinking of this matrix like this. I'm taking the top part, okay, B0j to B0n minus 1. This is a matrix, no? 1 by n minus 1 matrix. I'm going to think of this matrix as representing some operator T0, let's say, from W to span of V1. Okay, in the basis W1 through Wn minus 1. I can do that, right? So it's not too bad. It's just a matrix. So in a subspace of dimension, it can take a subspace of dimension n minus 1 to a subspace of dimension 1. It's perfectly valid. Same thing I will do with this other square part also. Okay, it's n minus 1 by n minus 1. So I'll think of it as representing a map T1 from W to W in that same basis. Okay, so this is just a comfortable thing for me to do. Now what it lets me do is the following. Okay, notice what has happened. If I take any vector v in V, that V can be written as V1 plus some W prime, where this W prime belongs to W. Okay, so this we know, because anyway these two are a direct sum, so I should be able to do this. Okay, so I can write like this. Now TV is T times V1, TV1, that is lambda V1, plus TW prime. Now this TW prime one can write as T0 W prime plus T1 W prime. You can see that that's what really happens here. When I write TV, I have T0V happening on top, taking me to the span of V1, and then this T1 happening below, which takes me to W, and these two will add finally, right? So the coordinates are going to add. So you had T0 W prime plus T1 W prime. Okay. Now what is T0 W prime? It took me to the span of V1. I don't know what it is. It will be some coefficient dependent on W prime, but it will combine with the first term. It will give me the V1. Okay, and then I will be just left with T1 W prime. So this TV can be written as something into V1 plus T1 W prime. So that's the crucial part. So you take V, you split it into something in V1 and W prime. TV also, this C1 will transform into something in V1 plus T1 W prime. Okay, these are all linear transforms. You can see what I've done here. It's not something very fancy, just basic arithmetic and carefully written down, observing what's going on. Okay, so this is sort of like quotienting an operator. Your book talks about it. I'm not using that language. I'm just briefly mentioning it for those who are interested, but this is just easy enough to describe in basic terms. So what I can do with T1 is, since I am in the complex field, T1 will also have a eigenvalue. Okay, that's what's very important. So T1 will have an eigenvalue. Okay, at least one eigenvalue is guaranteed. Okay, of course, if you use determinants, etc., you can do more things. But let's say we have one eigenvalue, and that eigenvalue I am letting it to be lambda 1. Okay, lambda 1 is that eigenvalue, and there will be an eigenvector W corresponding to it. Okay, so there will be a W such that T1 W becomes lambda 1 W. Okay, so this is always true for any operator. So notice what is the change of basis that I am going to do now. See, previously I was in standard basis, some basis. I went to this basis V1 W1 Wn minus 1. So okay, so this is yeah, so maybe from, okay, this is okay, but I mean I don't need to go from here to here. Basically I need to change basis to this guy. Okay, forget about this from, it's not so crucial. Okay, so you can think of it like that, but it's not so crucial actually, in my opinion. You can forget about it. You change the basis for T to this guy. Okay, V1 W W1 prime to W prime n minus 2. What are these things? See, V1 is the eigenvector for T itself, the one eigenvector I found. Okay, what is W? W is the eigenvector for T1. Okay, I found an eigenvalue for T1 and its eigenvector is W. I take V1, I take W, and then I expand to the basis for the whole vector space V. Okay, what will happen if I do that? You can go back and look at what has happened. Okay, if this W prime were to be an eigenvector, T1 times W prime will simply be lambda 1 times W prime. Okay, so you will get a form like this. So that's what's very important. So T times V1. So in this basis, T V1 becomes lambda V1. What will be TW? Okay, remember TW, W is an eigenvector. TW will be something into V1, I don't know what that is, plus I will have a T1W, and what is T1W? Lambda 1 W. Okay, so this guy simply becomes lambda 1 W. So I will have something here corresponding to this term. Okay, I don't know what that is, but the second term has to be lambda, and all these guys have to be 0 because it's an eigenvalue. So I've got my bunch of zeros here. So notice what I've done. I did it for T, I take care of the first column, and then I shifted down, pivoted down into the bottom n minus 1, n minus 1 part, and then applied the same idea again. I know I will get something on the top, I don't care, forget about it, but on the bottom I will get lambda 1 followed by zeros. Okay, and what you did here, you can continue over and over and over again, and you will end up in an upper triangular form. Okay, so that's the crux of the upper triangularization idea. Okay, so hopefully that was clean enough. Think about what I've done. So just exactly like you did elementary row operation, went from pivot to pivot, we're also doing that here, except that in every stage I'm finding the eigenvector. Okay, so let me go back here, sheet that I had, and we had done it for the first column, right? We got 55, bunch of zeros. Now let's move down to the next one. Okay, so now in Sage Math, this notation A1 of 1 colon comma 1 colon will give me the bottom 4 by 4 matrix. 1 onwards, 1 onwards. The coordinates start from 0 in Sage Math. So 1 onwards for the x coordinate, 1 onwards for the y coordinate, sort of rows and columns. So you get this bottom 4 by 4. Its eigenvalues, you see, remarkably, it's 55, 55, 55, 55. Okay, so it's not very surprising because you know why it should work out like that. Okay, and then if you look at the eigenvalue matrix, again I have one eigenvalue matrix, 1 minus 3 minus 3 2. Okay, so now I will take this and make a change of basis for my A. Okay, so notice what I've done here. I'm creating an S1, which is the new basis I go to. The first column, 1 minus 4 7 8 minus 6, that is the original eigenvector that I had for the whole thing. The next one, you see what I have done. I put 1, minus 3, 2, 2. Here I put 0, you can actually put what you like, but anyway, let's say 0 is good because it ensures linear independence and all that. And then I can extend. Am I extending it to the basis for the whole vector space here? Okay. And then I do just S1 inverse A S1. And notice what has happened. I've got my 55 here, and below that is all zeros. Okay. Is that clear? Now I repeat. Okay. So I've come pivoted down to here. There's no problem with the pivot being 0 here, right? So because this is not like a elementary row operation, I have to take this matrix, which is A2, 2 colon 2 colon, that is that matrix. You can see the eigenvalues 55, 55, 55. And then you can find its eigenvector, it's 1, 1, minus 1. And then I form my change of basis, which is 1, minus 4, 7, 8, minus 6, 1, minus 3, and then 0, 0, 1, 1, minus 1. And then I have the usual extension, and then I do S2, I get this. Again, I keep repeating. Okay, just the extension here you have to pay attention to. So here you got eigenvector 0, 1. So you got the 0, 1. The next extension cannot be 0, 0, 1. It should be 0, 0, 0, 1, 0. Okay, so just make sure the extension you pay attention to when you do this, when you construct this S3, you will get the S3. And lo and behold, you finally got an upper triangular matrix. Okay, so if you keep repeating this operation over and over again, you will end up in an upper triangular matrix. So I found one similarity transform S3, which when acting on A, S3 inverse A S3 gave me an upper triangular matrix. So this is the upper triangular matrix, which is equivalent to that other matrix. Okay, so hopefully this sage math. Once again, you can click on this link. Okay, it will give you a way to download the CoCalc notebook, and you can open it and see it. All right. So we saw the upper triangularization. So let's state it formally, right? Every linear operator over complex. Okay, the complex is needed because we need eigenvalues. If it's not complex, you don't know if eigenvalues exist. Has an upper triangular matrix representation. Okay, so the proof is to simply continue the previous process, one eigenvalue at a time. I showed you how the diagonal occurs, how the zeros occur below the diagonal, and you get an upper triangular matrix. Okay, all eigenvalues are on the diagonal in the upper triangular matrix representation. That is very clear. Okay, algebraic multiplicity of an eigenvalue is number of times it appears on the diagonal. Okay, that we know. We know the geometric multiplicity now has to be less than or equal to algebraic multiplicity. Why is that? You take an upper triangular matrix of T, okay, and then if you look at algebraic multiplicity of eigenvalue lambda, number of times lambda appears on the diagonal, right? So you take, okay, so just to proceed here, we finished with the upper triangularization. We know what upper triangularization is. Now we are going to proceed and look at diagonalization. When will that upper triangularization become diagonalization? That's the sort of thing that we are going towards. Okay, so for that, this algebraic multiplicity, geometric multiplicity, and all of them are very important. Okay, so once you get an upper triangular form, you'll see proving all these things will become very easy. Okay, so how am I defining algebraic multiplicity? We defined it before also. How many times the eigenvalue repeats? Once you get an upper triangular matrix, the values on the diagonal are the eigenvalues, so you can easily find the multiplicity. You can define them. Okay, now what is geometric multiplicity? You might remember it's the so it's basically, let me just remind you what geometric multiplicity is. Okay, so this geometric multiplicity is number of linearly dependent eigenvectors, right? So, or in other words, it's dimension of null T minus lambda I. Okay, so this is what it is, geometric multiplicity. Okay, so it turns out once you come up with the upper triangular matrix representation, it's easy to show geometric multiplicity has to be less than or equal to algebraic multiplicity. Okay, why is that? See, what is algebraic multiplicity? For simplicity, I will take the lambdas to be on top, and below you have zeros, and then you have a bunch of stars, right? So I don't know what's going to happen here. I don't know what's going to happen here, but I have lambdas here. Okay, how many lambdas I have here? That is equal to algebraic multiplicity of lambda. How many ever times it appears, it appears. Now when I do a minus lambda I, what's going to happen? All these guys will become 0. Okay, they will become 0 when you do a minus lambda I. Okay, so when they become 0, you can clearly see there will be a linear dependence on this side, right? So once they become 0, you have a linear dependence showing up. Okay, so you can see rank of a minus lambda I, the rank becomes greater than or equal to, Did I get that right? Yeah. So greater than or equal to n minus am of lambda. Okay, see when you have these lambdas subtracting, you will get a bunch of zeros here. So you have here n minus am of lambda. Okay, that many rows, and the rank has to be at least that. Okay, even from here, depending on these elements, you may get some rank, additional rank may happen, but the zeros have been knocked out, so you don't know if they will contribute to the rank. But the rank of this a minus lambda I has to be at least n minus whatever you knocked out here. Okay, now that tells you that this is true, right? So why is that? So because n minus rank of a minus lambda I. Okay, maybe I should write that down here. So n minus rank of a minus lambda I is less than or equal to algebraic multiplicity of lambda. And what's n minus rank? That is this guy, right? Dimension of null of t minus lambda I. Okay, so geometric multiplicity becomes less than or equal to algebraic multiplicity. Okay, so notice how the triangular matrix really simplified this for you. Okay, so if this were not a triangular matrix, then just because you knocked out something on the diagonal, you don't know what happens to the rank. But below that, the 0 is there, and here all these guys are non-zero, so you know that the rank is at least this much. Okay, so that's what's very useful in this result. So you can prove some nice results on geometric and algebraic multiplicity. Okay, so this is useful. You will see this will play a nice role in the diagonalization. So now let's define something called an eigenspace and then connect it up with diagonalization. So we've been talking about this null of t minus ai, t minus lambda I, t minus lambda I. Every time you have a lambda eigenvalue lambda, this null of t minus lambda I has all the eigenvectors, right? So it's very natural to define it as the eigenspace. So this eigenspace is like the invariant subspace corresponding to the eigenvalue lambda, and that's null of t minus lambda I. Okay, so that has a special notation. We'll call it E of lambda t. So basically, eigenspace is a set of all eigenvectors along with the 0 guy also. So we see the geometric multiplicity is nothing but the dimension of the eigenspace. We have shown that it's less than or equal to the algebraic multiplicity. Okay. So also notice dimension of this guy, which is geometric multiplicity, the number of the linearly independent eigenvectors. Here is a very interesting result. Any two eigenspaces can only trivially intersect. Why is that? Because if they have distinct eigenvalues, right? When they have distinct eigenvalues, then they can only intersect trivially because eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay, so you cannot have a non-trivial intersection there, and that would violate the linear independence of eigenvectors. Okay, so that's nice to see. Okay, so let's say you have a linear operator T and it has m distinct eigenvalues, lambda 1 to lambda m. Okay, the corresponding eigenspaces, let's say, are E of lambda 1 to E of lambda m. Okay, so I am looking at an operator. It has a bunch of eigenvalues. Some of them may be repeated. Maybe there are m of them. Each eigenvalue will correspond to an eigenspace. Now we can give a partial answer to sort of an interesting answer to, not actually partial answer, it's a good answer to when is a linear map diagonalizable. It turns out a linear map is diagonalizable if and only if these conditions are true. The geometric multiplicity for every eigenvalue should be equal to its algebraic multiplicity. Okay, if an eigenvalue is repeated so many times, there should be that many linearly independent eigenvectors. This is sort of like if and only if. If this is not going to happen, if any eigenvector is missing, right? If you have, it occurs many more times algebraically or on the diagonal of the upper triangular matrix, but it doesn't give you enough eigenvectors, then you cannot diagonalize that operator. Okay, there is no basis on which that operator will become diagonal. We haven't quite proved that fully in some sense in this class. I am not intending to. The textbook has a full proof. You can go take a look, but you can sort of intuitively see why this should be true. Okay, so if lambda appears so many times and the number of times, the number of linearly independent eigenvectors is not enough, then you're not going to really be able to find all these one-dimensional invariant subspaces, right, which will all add up to the whole V. Okay, you can notice here that when a linear map is diagonalizable, then the vector space becomes the direct sum of all the eigenspaces. Okay, so that's central to making this happen. Okay, so you have to have the geometric multiplicity being equal to algebraic multiplicity, and the vector space should be the direct sum of all these things. So notice what will happen. The algebraic multiplicities will add up to n. Right, they are on the diagonal. All the eigenvalues are on the diagonal. So you add up the algebraic multiplicities, you will get n. Now geometric multiplicity, if it is equal to that, sum of the geometric multiplicities will also be n. And these eigenspaces don't intersect non-trivially, right? So they trivially intersect. So the direct sum of eigenspaces gives you V. Okay, so this is a very nice picture to remember. Okay, so if you, when is a linear operator diagonalizable? There should be eigenspaces whose direct sum becomes equal to the entire vector space. In that case, the operator is diagonalizable, otherwise it's not. Okay. Another way of putting it is geometric multiplicity should be equal to algebraic multiplicity for every eigenvalue, then it is diagonalizable. Okay. So this sort of completes the picture of diagonalizable. You might naturally ask, what if it's not diagonalizable? What is the simplest form we can get? Maybe we'll get to it later in the class if there is time. Okay, but for now we'll stop here. This is a good place to stop. So in general, any operator you can upper triangularize. There's no problem. Okay, you will have an upper triangular representation. When will it be diagonalizable? If its geometric multiplicity is equal to the algebraic multiplicity. Okay, so that sort of concludes this whole study of eigenspaces, eigenvalues from a diagonalization and upper triangularization point of view. We will study it further using more interesting properties, etc. But for now we'll stop here. But before I finish this lecture, let me show you the last computational tool that I promised to show you, which is MATLAB. Very basic few commands. MATLAB is also very easy to use. You have this randi command which will generate a random matrix for you. I put a 8 by 8 matrix, and there is this eig command which will give you the eigenvalues along the matrix, diagonals of a matrix. That's why I put diagonal, and then the eigenvectors in B. So you can see this matrix is a random sort of matrix, and it has complex eigenvalues. Notice it has distinct eigenvalues. How many distinct eigenvalues? There are 1, 2, 3, 4, 5, 6, 7, 8. 8 distinct eigenvalues are there. So it is diagonalizable. I know that for sure, but it also has some complex eigenvalues. Notice complex conjugate eigenvalues are there, right? So it will be complex conjugate, no? You can also show that it will be complex conjugate eigenvalues. So that's easy to see because this is real, right? So determinant A minus lambda I will be a real matrix, real polynomial. So it will have complex conjugate eigenvalues. So you can see complex eigenvalues showing up. Okay, so in practice, complex eigenvalues are very common. Okay. So also notice another interesting thing. There's one eigenvalue which seems to be relatively very large, and all the other guys are sort of, slightly small. That's also something interesting. Okay. Now here are the eigenvectors. So you see the complex eigenvalues correspond to complex eigenvectors. The first one is a real eigenvalue, 27.20 something, and that corresponds to a real eigenvector. Okay, so you can see that here. And the other eigenvalues, the complex eigenvalues, correspond to a complex eigenvector. Okay. And then likewise you will have other things. And if I do V inverse AV, I get a diagonal matrix with the eigenvalues on the diagonal. So this is MATLAB for you. I have not been able to share it quite so nicely. You can look at the commands here, okay, from the slides, and then try it in MATLAB also if you like. This is just a simple few lines, so it's not worth sharing in great detail anyway. Okay. Alright, so let me once again remind you of what we looked at in this week's lectures. We looked at eigenvalues, eigenvectors, linear operators very closely, how to compute them, how to work with them, how to think of diagonalizing an operator, how to get a diagonal matrix to represent an operator. With the power of it, we saw that upper triangularization is always possible, but diagonalization in some cases, maybe most cases it would happen. And I showed you also 3 computational tools that you can use as part of this course to try out matrices by hand. I would urge you to try it out. Just pick up some random matrices, look at eigenvalues, see what they tell you, look at row spaces, look at column spaces, look at rank. Just get a feel for what they are really also. Okay. Thank you very much. That's the end of the lectures for this week. We'll meet again next week. Thank you.